All right, so we are on slide 14. Slide 14, we're covering limiting reactants. So a limiting reactant is a reactant that will run out first, and then once it runs out, you can't make any more product. And then that's the opposite of excess reactant. That's one that won't run out. And so when the limiting reactant runs out, there will be some excess of the excess reactant left over. Let's just do some practice problems. So what mass of C3H3N can be made when 1.6 grams of C3H6 reacts with 21.6 grams of nitric oxide? So when you're first given, so we're given 21.6 grams of this and 21.6 grams of that. So, and then we want to determine how much of this, the grams of this, right? But first of all, we have to determine which one's a limiting reactant. Although they have the same mass, well, you'll notice there's a couple of things. These are molar ratios, and they're different. And so therefore, we have to convert these to moles and then take a look at that ratio. The easiest way of figuring this out actually is, let's just determine how much of the final product that each will make. So if I just had 21.6 grams and I had an unlimited amount of NO, how much of this would I make? So 21.6 grams of C3H6 would make how many moles of C3H3N? What we're trying to do is we're going to try to compare how much each makes, how much product each makes. So I'm going to convert this to moles of C3H3N. So this is 18.07 grams of C3H6, 1 mole of C3H6 times, so for every 4 moles of C3H6, there's 4 moles of C3H3N. Okay, so we calculate that, 21.6. So this is 1.19 moles of C3H3N. All right, now we're going to do the same thing, but now with the NO. So what about if I have 21.6 grams of NO? How many moles of C3H3N would I produce? So here's a molar mass. I'm converting to moles of NO first. And then for every 6 moles of NO, I have 4 moles of C3H3N. So 20, 30. So what I want you to see is that 21.6 grams of NO makes less moles of C3H3N than 21.6 grams. So this will be the limiting reactant. And then this is the excess reactant. Because once we make 0.480 moles of C3H3N, there's going to be no more NO to use with the rest of the C3H6. And so that ends up being our limiting reactant. Now I want you to notice that before, when we just had the mass of each, we couldn't tell which was our limiting reactant. Why? It's kind of like you have to compare apples to apples, right? If we have moles of C3HN and moles of C3HN, we can clearly figure out, oh, this is how many moles 21.6 grams of C3H6 is going to produce. This is how many moles of 21.6 grams of NO is going to produce. Okay, it's easy to see, oh, that's the smaller amount, or has a lower amount of product, therefore it's going to be the limiting reactant. The final question was, what is the mass of C3HN what can be made? Well, now the key is, whenever you do a problem, you always have to use a limiting reactant. Why? That's the one that's going to run out first. It's the one that limits the product that's made. This is the only amount of product that can be made. Yes, there's going to be leftover C3H6, but there won't be anything to react it with, because why? All the NO has run out. All right, so we have moles of this, so we can just merely take the moles of this and then multiply it by the molar mass. So for every 1 mole of C3H3N, what is that? 0.01. So if I multiply that by 0.480, so it's about 25.5 grams of C3H3N. Okay? All right. Next one. It says if 3.20 grams of iron 2 hydroxide is reacted with 2.50 of phosphoric acid, what is the limiting reagent and what is the reactant in excess? We have 3.20 grams of this and then 2.50 of a phosphoric acid, right? And so we got to figure out which one's limiting reactant. The way we do that, like last time, is we're going to convert these into the product. We're going to see how much each can make in the moles of that product. My suggestion is, if you look at the next question, a lot of times there's like multiple questions. Eventually, we want to figure out the grams of iron 2 phosphate. So eventually we want this. So I could have picked this, or the water, or the iron 2 phosphate to compare. But I'm just going to choose iron 2 phosphate because of this. Then I can use this, right? I can use the iron 2 phosphate. I can use the answer from determining the limiting reactant in the this second answer. So I chose this product to compare iron 2 hydroxide and phosphoric acid. So 3.20 grams of iron 2 hydroxide So got to figure out the molar mass. Iron, I think, is 55.85 plus 32 plus. Oops. So this is grams of FeOH2. Then we didn't balance this equation, did we? Well, you got to balance the equation first, don't you? So let's balance this quickly. Oh, this is going to be interesting. So for sure, we're going to have a 2 here. And we're going to need a 3 here because of the iron. So that gives us 6. That gives us 6 OHs. So we're going to at least need the 6 here. So 6 is here. Alright, so now we can, got to remember to balance that equation. So for every 3, we're going to Alright, so let's do this math. 3.2 divided by 89.87 divided by 3. So this will produce 0.0119 moles of Fe3PO42. You got 2.50 grams of phosphoric acid. So phosphoric acid is, phosphoric acid. Hey, what's the molar mass of phosphorus, you know?
31.
31, cool, thanks. 0.03 plus 4 times 16. So 98.03 grams of H3PO4. 1 mole of H3PO4. And so for every phosphoric acid, every 2 moles of phosphoric acid, we have 1 mole of iron 2 phosphate. 2.5 divided by 98.03 divided by 2. 0.0127, so that's 8 moles of iron 2 phosphate.